Are we ready to start? So good afternoon, everybody. Thank you for coming to this presentation. My name is Jean-Marie Verdun. I'm the CTO of ITRENEW, which is a Silicon Valley-based company. I am there with Julien Viard-de-Galbert, who is a firmware engineer at ITRENEW. If you wonder from where we are coming, we are French. That's why we have a long and complex first name. We are going to speak about testing firmwares and why open source firmware are really key to our activity. So ITRENEW is a leading provider solution provider for a circular economy and dedicated to data center operation. We serve clients like Facebook, Microsoft, and many of the hyperscaler companies that you know around the world. And our primary goal is to provide them technology, logistics, and monetizations of their disposal assets. And to do that, we developed a program based on the Open Compute project called OCPSummit19 that intends to sell secondary within the secondary market servers. And we have a recertification program which does include the fact that we can provide high-level services, including security services and the fact that we can upgrade firmware. So that's why open source firmware are really key to our activities. Just looking at the goal of the linuxboot CI that we intend to develop, we are willing to automatize as much as we can the firmware testing process. That's mostly because we would like to avoid any human mistakes, especially at the firmware level. And to do that, we are expecting to build up a full open source stack. And the CI that we intend to develop is targeting two kinds of firmware. It does include linuxboot and OpenBMC. So we are really seeking at open source firmware, which does include the BMC controllers and the system BIOS technology. So the main principle of the CI is to be automatized, and it is based on the web API, so which is public. You can find it on the GitHub account of the linuxboot currently. And there is a job controllers, and the job controllers is running in sequential the testing operation. So the first step is a builder. The second step is to validate that the firmware that we just built doesn't break the node. And if the node boot up, we are testing the basic features, like did we lost any system configuration, like PCI Express bifurcations, does NUMA run properly, or any kind of low-level features that you are expecting from your servers. We are also validating that the PCI Express configuration is properly set up, so especially on the machine where the bifurcation should be turned on. If the basic features works, our goal is to validate that we can boot up an operating system properly on top of the firmware, and that's a really key features from the server. And we run the stress test on top of the machine to validate that the firmware is implementing all the necessary features that the operating system is expected. The CI is currently running on OCP node, and we are targeting to release it fully, probably by the end of the year. We do have some implementation. So what kind of technology are we using? So we basically build up the CI to be scalable by itself. So we use Ansible to pre-configure the basic infrastructure which is needed to run the CI. And this is the provisioning part of the CI. Then we use automatic redundancy and scalability based on hardware availability, and this is performed through Slurm. So roughly, we are using technologies which are coming from HPC world. So we build up clusters, and based on these clusters, we are launching job and batches. And these batches does represent each step of the CI. Following the Slurm batch, so we use key VM to run VMs for building all the steps of the CI. So we build linuxboot within a virtual machine, and we also build the operating system images which are needed to run on linuxboot and the OCP servers. So you might be aware that the OCP servers are using IPMI interfaces, or OpenBMC is providing serial over LAN console. Just to support that, we need to pass some specific kernel argument and being sure that we reroute the console to the right TTY. And in some cases, it does require us that we tweak the operating system installers, and we are waiting just to be sure that we can install properly Ubuntu or Red Hat or any kind of flavors of Linux on top of linuxboot. The basic setup, so if you want to build up your own CI systems in-house, it does require an Ansible master node, a Slurm controllers, a Slurm batch node, and then after the target nodes on which we are going to run the batches. So you need at least 4 different servers plus network switches to make run properly that software. It's not that complex, but you still need the basic stuff to turn it on as a functional implementation. So we are going to go through the various components of the CI. So we do have a public web API. The goal of the web API is to control each step of the process. So we can launch a job. So the job might be a linuxboot compilation, and then after a linuxboot load on the node, and checking the status, and sending command to a node. This is work in progress, by the way, so if you are willing to enhance the CI, feel free to join the community and send us feedbacks. We also provide the build log, which is something very important. Right now, as an end user, you cannot connect to a node if something goes wrong. That's a feature we would like to implement just to check what happened bad. The initial implementation is written in Go. This is just to fit with the UTK environment, which has been introduced by Gan and and Ryan. So we currently support job launch, status query, and log, and we are expecting to enhance all of this later on during the year. The job controller is able to allocate build nodes, is able to preset the build environment, and is also storing the job status. And this is also used to control everything which is going to happen during the CI runs. And the initial implementation is based on Slurm, as I said. We are currently using an aging build environment which is based on Ubuntu Xenial. I am the lead developer on that side, so I'm thinking about upgrading from Xenial to Bionic, which is the latest long-term support Ubuntu implementation. So if some people in the room wants to help me to do that, feel free to ping me just after the discussion. The basic build environment use 2 kinds of builds. So as we are keeping building linuxboot images or installers, so we offer the possibility to either run build in memory, just to avoid to kill either the SSD drives or being dependent on the I/O speed of the build nodes, or build using local storage, which is based on hard drives, so it could be slow. The maximum build that we can do in memory is about 40 gig, so we are trying to enhance that to higher memory size, just to avoid that we spend too many times on waiting for I/O. The remote access to the VM is not yet implemented, but we are getting the logs files from Slurm. So if something goes very bad during the build, so you will get all the information, and we have to restart the whole build just to be sure that things are moving forward. So the builder is currently based on HIDS, and we are expecting to move to UTK pretty soon. So just to let you know, HIDS was the original build implementation for linuxboot. It was based on a bunch of Perl script, which has been provided by 2 Sigma developers, or Trammell Hudson, who is not there, unfortunately, today. And these build scripts were just a bunch of scripts, and the community decided that we needed to restart from scratch and re-implement that through UTK and Fiano, just to be sure that we can maintain the script using Go. So right now, the initial implementation is still based on heads. That's the works that we need to do during the next couple of months. But to move to UTK, the build is working for the Winterfell machine. So this is an aging OCP servers. But it's pretty efficient and works pretty well. So we can build linuxboot kernel using the 4.9 version. And we are using the nerf u-root environment as a user space for linuxboot build. We can control and extract the Dixie drivers. And this is features that we are going to extend with UTK integration. And we can generate the final Linux boot ROM, and we can get it back to the controller node and use it for later on usage on the working systems. So the node brick validation is the following step after a build. So we try to automatize the fact that we can test a generated ROM. So to do that, we are tweaking hardware. So we interconnect flash emulators to OCP servers. So to do that, we need to unsolder the flash from the motherboard and get connected to the SPI bus, which is directly linked to the Xeon CPUs and to the flash emulators. One of the benefits of the flash emulators is that we can load through the flash emulators a new ROM within a couple of seconds, well below 10 seconds. So which is far much faster than using either the BMC interface, which can last for 10 or 20 minutes, depending on the systems. And it is valuable, so that's super efficient, especially for CI build. And we are discussing with the server community just to try to get a better way to interface flash emulators on a regular basis on OCP servers, because it's highly frustrating just to have tweaking hardware to get connected to a 2-pin bus, roughly, or 4-pin bus. So the goal of the node brick validation is to test the firmware image on real hardware. It's really key. So even if we can test on QEMU the features, so it's always important to validate on real hardware if we are breaking a node or not, and if the features are turned on normally. And this is currently working, and we are going to try to make a demo during that talk. Hopefully it will work. The feature validation is under the Linux boot environment. So we are using an extension of the nerf code, which has been provided by Ron Minnick at Google. So that's a way to try to connect to the Linux boot image and try to get feedbacks. That's a work in progress currently. This is the target that we are expecting to reach. We would like to be sure that we can properly boot on NVMe and that ASCII controller are properly set up so that all the I/O are basically properly configured under Linux boot. And this is something which is also key. And then after the last step of the basic feature validation of the firmware image is to validate that we can boot under an operating systems. And we are testing at least 3 modes, which is the networking boot through Pixie. And Julien had a demo on the ITRENEW booth, by the way, with a networking boot and the Debian installer. And that's something which works right now. And then we try to boot on local ASCII controllers and NVMe, which are the basic I/O subsystem that everybody uses currently. Everything is also based on Ubuntu Xenion currently. That's probably something we need to update to support latest generation of hardware, especially the Skylake servers. So we regenerate a full ISO image. We reroute the console to the IPMI of the servers. It's really key. The second step is really key because just to get feedbacks from the status of the node, we need to get access to the IPMI interface. And we validate that we can boot the image through the Pixie process. The OS stability and stress test, this is the goal. So currently nothing is implemented. So if you want to work with us on that, feel free to join the community and provide us helps to implement that. What we have observed is that we need to validate that the firmware doesn't break anything, like VMX, which is the key VM support and the virtualization extension on Intel CPUs. If the hyper-threading works properly, if the CPU frequency management works properly, the power management, the NUMA, all of these are basic features that you are expecting to work on the servers. They are pre-configured by AMI system BIOS, and they are in some way broken by the linuxboot implementation, or they are not properly supported. So roughly, the CI intend to avoid that a new patches within the source tree of linuxboot is going to break features which you are expecting to work. And all of this another time is expected to be done automatically. We are expecting also to test basic PCI interface. And if you would like to extend that list, just ping us. So we are currently testing or expecting to test 10 to 100 gig network adapters, Lightning and NOx. So this is hardware that we have hands-on, so it's pretty easy for us to turn on this hardware and put it inside the CI. And then we are expecting also to run performance benchmark to validate that we do not break or we do not have performance decrease with a new version of the firmware. So we does include the NINPAC, we does include networking speed benchmarks and Bunny for higher speed. And we are expecting to launch VMs on top of the servers. So we think we might be covering all the subset of the basic features that the servers is doing during production. Another time, the benchmarks are very basic benchmarks. So we need contributors to expand all of this because it does require a lot of time just to turn on and validate that everything works. So how does the CI work as of today? It's pretty small, in fact, on the script. So just to launch and create a CI job, so you need to have a GitHub repo with a CI configuration file, which is based on YAML. And the CI configuration file is roughly a script, which is going to describe what kind of tests you are expecting to run. And then you have to submit the script through a curl interface to access the web API. So this is a very basic implementation. So to control a node, to control an execution and validate it that everything works, we got various ways to do that. So you still use curl, and then you get the options on that slide deck. And you can retrieve the results and to get the complex output that your build might be generated. So Julien is going to try to run the demo now. I hope the internet access works because the demo is going to be run from a machine which is hosted in Paris, France.
Okay. So I try to connect. Yeah, connected. So here it goes. So on the right, I'm gonna put a terminal. So that terminal is will be displaying the console of the server. And on the left, I'm gonna launch the command that the CI would launch. So I'm going to load the image and install it. Yeah.
Is it better?
Is it better? So here it's loading the image into the Flash emulator, and at the end it's pouring on the node. Can you make that one bigger? And on the other screen, we'll get the traces of the kernel booting. It was working this morning. Yeah, it's working. So the first starting linuxboot is the end of the Dixie phase. And here we have the kernel. So that kernel is the kernel inside the flash booting, actually the flash simulator. And here we are in a shell that's from uroot. So I guess Chris will tell you a lot more about linuxboot as it's the next talk. So basically here, everything is automated through scripts, but could be integrated in the CI environment that Jean-Marie just described. So we can change the flash and do a test. So for people that were here at the previous talk, using the tool for the question you had, using their tool to remove Dixie one by one could be automated with that.
Yeah, what is key into this demonstration is that we get connected on two servers. The one on the right-hand side was fully turned off and was part of the cluster of the testing clusters. And the one on the left-hand side is a controller node. And they are hosted in about 10,000 kilometers away. So as being a firmware engineers, you can now develop your firmware on your laptop, generate image, push that to data centers through automatized scripting, and just get feedback on the fact if your new firmware image works properly or not. So this is definitely something you cannot do with the regular EMI testing tools, which are the proprietary tools on firmware. And the other main benefit is that as we are under Linux, on linuxboot, we can validate many things which are related to the Linux kernel, and we can check that everything works properly. So this is the main benefit of the CI, using the emulators, hitting fast, testing in a much faster way, and there is no human interactions during the testing process. So that's really key, because this is avoiding that any mistakes appears, and this is avoiding that we release in the wild firmware which might be containing security issues or performances issue. So what's next? These machines are proof of concept that we hosted in Paris office, and as we are now part of the new ITRENEW, as I said at the beginning of the talk, we are expecting to expand that process and put it on an industrial stage. So we are opening a community labs in the Bay Area, where we are willing to host another CI environment, which will help us to scale. So as of now, most of the servers which are used in the CI in Paris are based on Winterfell. So we will be expanding to Winterfell and Neopar in the Bay. So Winterfell doesn't support OpenBMC, which was pretty tricky to us to integrate OpenBMC into the CI environment. So we are going to have Leopard nodes. And when I say we are going to have, the community is going to have access to this node. So meaning that the ideal use case will be that each time there will be a commit on the linuxboot GitHub repo, this is going to launch on the public CI a job, and this is going to validate that this commit is not going to break anything on the firmware level and the server level, just to validate that everything works. We are still really far away from that, so I think there is still probably 6 to 12 months' work just to have the basic full stack working. But this is the main goal, and if you are willing to help us to build it up, just let us know. So we work very closely with GAN teams and the other linuxboot community members, but that's a lot of work. We are also expecting to host some meetup, and I think it's really key that we hold sync up and validate that the API is properly understood by all the developers. We do contribute to open source firmware, so right now we are also hosting some build nodes for the OpenBMC, and we are always seeking for new contributors. And you can contribute to the linuxboot CI just by committing code to the linuxboot GitHub repo. So this is roughly the end of that talk. I don't know if you have any questions.
How do you envision testing the OpenBMC product? Because this is on the speed, which is not easy to operate. I mean.
Yeah, roughly we're expecting to test it the same way than we are testing linuxboot. So we are expecting to change the flash chip by a flash emulator and load the BMC image within the flash emulators, turn on the BMC, and when the BMC is properly booted, so we can turn on then the system. We are definitely tweaking the hardware. So, and as the flash emulator is under the control of a different node, if something goes wrong, we can automatically reload another image. So that's always the pain when you are developing firmwares, when you break the nodes and you need to recover it. So we are just trying to avoid a recovery phase by using emulators everywhere. Any other questions?
So if we have any errors or generate any errors during the process, are you writing that to a file that access?
Yeah, the first step is getting access to the log file of the build and the testing. And when we will be fully integrated within the GitHub process, so the GitHub process, when you launch a CI job, is expecting a return status from the CI jobs. So we are expecting to use that process, just reporting the CI job status within GitHub, and the developers can get that status directly through the pull request is just as made. Any other questions? Thanks for your time and your patience.